Hello everyone, I hope that you and your loved ones are safe. Welcome to my talk. Exact queries match the query patterns with the data, and if nothing matches exactly, the query will not retrieve any results. As an example, in Google one can ask for the Nobel Prize winners in literature. It will retrieve a previously curated list of all the winners, including their name, the year they won the award, and a picture of them. If we complicate the query a little bit, for example, requesting for the Nobel Prize winners in literature that have fought in a war, since there is not a document that curates the list of such people, the results will not be satisfying. In that case, we can go to an external query service, such as Wikidata, in which we can ask for the Nobel Prize winners and for those that have fought in a war. The results of the previous SPARQL query are shown in this slide, which include famously Winston Churchill. On the other hand, similarity queries retrieve objects that are similar to the query, not necessarily matching exactly. On the web, one can ask for similarity queries. For example, to obtain books that are similar to Harry Potter. It will retrieve user-curated lists of books that are similar to Harry Potter. The similarity in this case depends on the author criteria. We can also ask a little more complicated queries regarding similarity. For example, obtain Latin American countries that have a similar population and GDP to Ireland. The results of this query contain a list of Latin American and Caribbean countries by GDP, but not in comparison with Ireland. In fact, some of the results don't even include the word Ireland on them. This brings us to our work, extending a SPARQL with similarity joins. First, I will present the goal of this work, which is to provide the users with the means for executing similarity queries in the context of the semantic web. Next, I would like to introduce some definitions. First, in terms of similarity. Similarity amongst objects depends on many factors, including the goals of the application, human appreciation, semantic contexts, and many more. In this slide, we present you with a picture of a corgi, a cat, and a dachshund. Is the corgi more similar to the cat or to the dachshund? Any answer to that question can be justified by different interpretations on the word similarity. Given this scenario, we will focus on distances as a measure of similarity, mainly metric distances. We will consider in this work that two objects are as similar as they are close in their metric space. A relevant operation in the context of similarity and similarity search is the similarity join, which, given two datasets, their similarity join will contain all pairs of objects that are similar to each other, one of each dataset. There are two main kinds of similarity join. The first one is the range-based similarity join, which takes the two datasets and retrieves all pairs of objects such that the distance between them is of at most a given parameter r. So for each blue point in this slide, we will retrieve all the red dots that are contained in this query region. The other kind of similarity join is based on nearest neighbors, which for every blue object will find the k other objects in the red dataset that are the closest to it. So for example, in this blue object and given a k of 3, we will obtain the three nearest red objects to every given blue object. Note that a brute force algorithm that computes a similarity join will verify that each pair of objects satisfy the similarity criteria. This algorithm is called a nested loop. As a running example, we will use the following. To find all the pairs of Latin American and European countries that have the most similar GDP and Human Development Index, we will parse these objects into a two-dimensional space of GDP and HDI, and for each Latin American country, we will pair it with the closest red country, in this case, European country. So the result of the similarity join between the red and the blue sets will be the following. Now to our proposal. We propose to extend SPARQL in order for it to support a similarity join operator. In the literature, we highlight three works that are closer to ours. The first one is DBSimJoin, which is an extension for SQL that provides multidimensional range similarity queries using a subquadratic algorithm, which means they do not implement a nested loop. The second work is iSparkle, which is built on top of SPARQL 1.0. It allows for single-dimensional range-based similarity queries in a quadratic time since they implement a nested loop. The third one is mSimJoin. They allow for similarity joins between entities, semantic similarity join between entities of different datasets. And finally, we have our proposal, which is Similarity Joins SPARQL, which provides multidimensional, both range-based and nearest neighbors-based similarity queries, and it provides subquadratic strategies for the similarity join solution. We will review all the steps of the query evaluation pipeline, starting with the query writing, for which we propose an extension to the grammar of SPARQL, adding a new node to the group of graph pattern not triples group, which is this similarity graph pattern that includes the novel keywords similarity join on, top, within, and distance. Building on top of the similarity join between Latin American countries and European countries based on their GDP and HDI, we have that query represented in the extended SPARQL. Here we have the two triple patterns that obtain both sets of countries along with their GDP and their HDI, and in the middle part of it, we define the different parameters that are required to solve the similarity join. Next, in the query evaluation pipeline, we parse the query written in this extended grammar, and we parse it into a set of operators, including our new algebra operator, the similarity join, which has two versions, one for range-based similarity joins and one for nearest neighbors-based similarity joins. Then we attempt some optimization strategies in order to improve the performance of the evaluation of the queries. For this, we attempt to cache the results of the overlapping triple patterns of each part of this query. In this case, the part of the queries that obtain the countries, their GDPs, and their HDIs. So that set of triple patterns it's computed only once. Preliminary experiments show that this optimization does not impact very much in the performance of the query, so we opt for drop it. Finally, we go to the execution phase of the query, where we actually evaluate the similarity join. We propose three different similarity join strategies. The first one is the brute force algorithm nested loop. The second one is a tree-based index called the vantage point trees. And the final uses an external library that provides several algorithms for approximated nearest neighbors, which is called FLAN. We compare these three strategies. We took then 1,000 scenarios from the characteristic sets from Wikidata, having a varying number of entities and properties, and we perform a self-similarity join using all the properties of each characteristic set, where we can see that the brute force algorithm performs various orders of magnitude worse than the other two alternatives, which are very competitive to one another. Finally, we have the result iteration, where we go through all the resulting mappings and their distances. Now, I will present three use case queries that highlight different aspects of our proposal. The first one is an extension of our running example of country similarity. Here, we join all the welfare indicators of the Latin American countries with the European countries and computed Manhattan distance using those dimensions. Here we find that, for example, Romania is more similar to Peru, Portugal to Chile, and Turkey to Mexico. In the second one, we use aggregated dimensions. This is to show that not only we need to extract the dimensions from the data, but we can create our own. In this case, we are trying to obtain similar elections in terms of the number of candidates that participated, the number of political parties involved, and the number of political ideologies. And here we found that the most similar pair is the 2017 German election and the 2000 Russian presidential election. Finally, we ran a similarity join using images taken from Imagepedia. Here, we obtained images of churches that are the most similar to the US Capitol building. Here in the left, we see the images of the US Capitol, and on the right, we see the most similar images based on a border descriptor. We implemented this proposal on top of Apache Jena. Apache Jena is an open source SPARQL engine and RDF storage system. Our implementation is integrated in Jena in such a way that it only takes control over the evaluation of a query only if it contains a similarity join. We implement the different strategies that were discussed before, and the result iteration follows the fetch as needed philosophy of other operations, which helps us to avoid the storage of a possible quadratic number of intermediate results. We evaluated our proposal by comparing it to iSparkle and DBSimJoin, which we will review now in a little more detail. iSparkle introduces the imprecise blocks that allows users to compute distances between given attributes. In this case, for example, we have distances between titles and book titles, and they store, for each computed distance, they store a virtual triple containing the two objects and the distance. On the other hand, DBSimJoin is an extension of SQL, and it implements the quick join algorithm, which, given a dataset, it takes two pivots and defines a ball. Then it divides the objects into those that lie within the ball and those who lie outside the ball. Yeah, and it gives window partition in the frontier of the balls in order to maintain those objects that are similar to each other but that end up in different groups so they can stay together. Then they repeat this process recursively. When compared to iSparkle, our implementation presents the following advantages. First, ours is more efficient because it avoids nested loops. Secondly, our implementation requires less memory. It avoids the storage of virtual triples. Finally, it can handle an arbitrary number of properties instead of using pairwise property similarities. Finally, to compare to DBSimJoin, we use the same data and setup that's described in the DBSimJoin paper, and we used increasingly larger values for the search radius. When we compare the search radius to the execution time of the query, we see that our implementation increases the execution time more slowly as the radius increases than DBSimJoin. In fact, DBSimJoin stops working after R takes a value of 0.4. Then it crashes and it will no longer retrieve any results. On the other hand, when comparing the number of results of the query to the execution time, the curve for DBSimJoin is several orders of magnitude much more steep than our implementation that grows much more slowly than DBSimJoin. To finish this work, I will review some of our conclusions and future work. We have presented the design, implementation, and evaluation of a system that supports similarity queries over RDF datasets. We propose a novel syntax and semantics that adds a similarity join operator to SPARQL. We provide an open implementation of similarity joins on top of Apache Jena. We illustrated several use case queries, and we show that this system outperforms related works. We have a set of lessons learned from this work. The first one is that similarity joins seem to be an useful feature for SPARQL. The second is that range queries are usually unintuitive in abstract metric spaces for users, so providing k-nearest neighbors based similarity joins is key. However, it is much harder to implement. Finally, we see that syntax might be tricky to define, especially since similarity join require the definition of many parameters. We also see that similarity joins can take up to quadratic time, but we show that their computation is feasible in practice. A SPARQL RDF setting raises unique challenges for similarity queries, namely the need for normalization, the consideration of unbound, missing, and multiple values, etc. And it would be interesting to see similarity joins adopted in future versions of SPARQL, especially since version 1.2 is being discussed right now. As for the future work, we would like to perform experiments on the usability of the syntax and the system compared with standard SPARQL. We would like to experiment with different query rewritings and other query optimization techniques to see if we can further improve the performance of the evaluation of these queries. And finally, we would like to find other relevant use cases or domains that can benefit from these tools. So any ideas that you might have are always welcome.